Hi students, today we will look at the third topic under the course titled Alternative Transportation System, CEC 412. Today we are going to look at runway orientation and number. So the first thing we will look at is the relevance of metrological studies on runway design. Several factors in aerodrome design, such as runway orientation, runway length, wake turbulence, visibility, and environmental issues are closely related with metrology. So these factors are metrological factors, and on this section we are going to look at the importance of metrology in the aviation, especially in airport design, rather than forecasting the weather for pilots and air traffic controllers. It is important to note that a minor mistake could result to hazardous situations, which may also result in death or damage financially. It is important to note that a minor mistake could cause hazardous situations, which may result in death or damage financially. A crosswind component, fogginess, wind distribution, environmental management, obstacles, and winter conditions should be analyzed before designing a new airport. In addition, all the observational data obtained from the nearest metrological stations should also be examined in detail. So we look at the ICAT recommendation for runway design. For the crosswind, a usability factor of the aerodrome is not less than 95%. However, where the prevailing wind and crosswind conditions are not allowing to provide the percentage, the crosswind runway is required. So most times the wind should permit the runway to be used by the aircraft 95% of the year, or where it is not necessary to obtain such from metrological studies, then a provision should be made for the crosswind runway. The data of the wind speed and the direction, which is used for the calculation of the usability factor, should be as long a period as possible, preferably of not less than 5 years. These are recommendations according to ICAT. So for the parallel runways, where parallel runway non-instrument runways are intended for simultaneous use, the minimum distance between their center lines should, according to ICAO, be 210 meters where the higher code number is 3 or 4, 150 meters where the higher code number is 2, and 120 meters where the higher code number is 1. Where the parallel instrument runways are intended for simultaneous use, the minimum distance between their center lines should, according to the International Civil Aviation Organization (ICAO), be 1035 meters for independent parallel approaches, 915 meters for dependent parallel approaches, 760 meters for independent parallel departures, and 760 meters for segregated parallel operations. So the next thing we want to look at is the use of windrows method in the determination of the number and orientation of runway. Runway orientation. The orientation of a runway. The use of windrows method in the determination of the number and orientation of runway. The first thing we look at is the runway orientation. The orientation of a runway is defined by the direction relative to the magnetic north of the operation performed by the aircraft on the runway. Typically, but not always, runways are oriented in such a manner that they may be used in either direction. It is important to orientate a runway in such a way that operating in one direction is precluded, normally due to nearby obstacles. In addition to obstacle clearance consideration, runways are typically oriented based on the area's wind condition. As such, an analysis of the wind is essential for planning runways. As a general rule, the primary runway at an airport should be oriented as closely as practicable in the direction of the prevailing wind. When the landing and taking off aircraft are able to maneuver on a runway as long as the wing component at right angle to the direction of the travel and crosswind component is not excessive. So most times we should be conscious of crosswind component for aircraft. So we must make sure that the crosswind is not excessive because it could affect the operation of the aircraft. The Federal Aviation Administration recommends that runway should be oriented so that the aircraft may land at least 95% of the time. So most times we prefer to orientate the runway in such a way that operating at one direction is precluded, normally due to nearby obstacles. When the wind coverage is less than 95%, a crosswind runway is recommended. This allowable crosswind is 10.5 kN or 12 miles per hour for airport reference codes. So ICAT also adds that runway should be oriented so that aircraft may be landed at least 95% at the time with crosswind components of 20 km, which is 23 meters per hour for runway length of 1,500 meters or more. 13 km, which is 15 miles per hour for runway length between 1,200 and 1,500. And once the maximum permissible crosswind component is selected, the most desirable direction of the runway for wind coverage can be determined by examination of the average wind characteristics at the airport. So there is an instrument used for determination of or orientation of the runway, and this instrument we call it the wind rules. So the appropriate orientation of the runway at any airport can be determined through graphical vector analysis using a wind rules. A standard wind rules consists of a series of concentric cycles cut by radial lines using polar coordinate graph paper. So here we have example of a wind rules. So we normally draw a wind rules on a paper. So and it consists of concentric cycles. So when we say series of concentric cycles, these are the concentric cycles, these circular cycles we have here, and these ones are the ones which cut the concentric cycles. We call it the radial lines. These are the radial lines. These cycles shows the magnitude of the wind, while the radial lines shows the direction of the wind. So these are the direction of the wind. We have north, north, northeast, north, north, northeast, east, northeast, and so on and so forth. So while this is a transparent paper we use to determine the direction where we have the highest magnitude of wind. So most times we ensure that it does not exceed 15 miles per hour. So that's why we're able to divide this transparent paper. Half of it is calibrated as 15 miles per hour. So here we say the radial lines are drawn to scale of the wind magnitude such that the area between each pair of successive lines is centered on the wind direction. So when you place this on here, or you impose it on here, you'll be able to measure the direction of wind from different directions. You'll be able to get that, because this transparent plate or template placed here can make the visibility of the things that are calibrated in this cycle. So this cycle, like I said, are this magnitude of the wind. You can see here we have 15, 20, 25, 35, and we have 4 here, and here you have the wind directions. So this is a typical diagram of the wind rules coordinate system and a template. This template is used for determination of wind direction and orientation of the runway. So a typical wind rules polar coordinate system is shown on the left hand side. That's what we've just seen. The shaded area indicates that the cross wind comes from the southeast. So you can see it from here. This is a shaded area. You can see it comes from southeast. with a magnitude of 20 to 25 miles. This is, you can see here, this is 20. It ranges between 20 to 25, because from here you can see this is 20, 25. So when you move it down here, you see the maximum is 25, the minimum is 20. So a template is also drawn to the same radial scale representing the crosswind component limit. A template drawn with a crosswind component limit of 15 miles per hour is shown on the right hand side, as we have seen here. Okay. On this template, 3 equally spaced parallel lines have been plotted. The middle line represents the runway center line, and the distance between the middle line and each line is to scale the allowable crosswind components. The template is placed over the windows in such a manner that the center line on the template passes through the center line of the windows. By overlaying the template on the windows and rotating the center line of the template through the origin of windows, one may determine the percentage of time a runway in the direction of the center line of template can be used such that the crosswind component does not exceed 15 miles per hour. Optimal runway directions can be determined from these windows by the use of template typically made of transparent strip material. So when you go back, you see that we pick these windows. Here we have these windows consisting of concentric cycles cut by radial lines. So we pick this template and place it in such a way, because half of this template is 15 miles per hour. So we are trying to ensure that the crosswind component does not exceed 15 miles per hour. So we pick this template and put it, superimpose it on here in such a way that the center line, which represents the center of the runway, matches here, and from there we can rotate it. We can move it this way or move it this way. So as we continue to move it, we try to check, because this template will be able to cover from here, this direction to here. So what we need to do is we allow it to, we try to superimpose it, just as we're going to see from the next diagram. We have this, you can see what we have here. Okay, let's take an example in such a way that here we have an example where we are given wind data. You can see the data here where we have sectors. These are the angles in north, northeast, and so on. So this is a through azimuth angle, the radial bearing, and as the magnetic bearing. So here you can see our sectors or our wind speed range. Here we have between 4 to 15. We have these values. Between 15 to 20, we have these values, which is percentage of time the wind is blowing. Then we have 20 to 25. You can see the values we have. 25 to 30 we have, and this is our total. So we're trying to plot this. Plotting this here, you can see, let's look at the first one, northeast, because you will use a compass to plot the direction of the wind. You can see this very one is larger than this. You're going to plot it to scale. Why is this very one larger than the rest, and the last one is larger? So what we have to look at, we try to look at here from the table. We have between 4 to 15. The range is 4 to 15. This is 15 to 20, which is 5 interval, unit of 5. This one is a unit of something higher than 10. This is 5 to 15. The difference is 15 to 20. The difference is 5. 20 to 25 to 25. The difference is 5. 25 to 30. The difference is 10. So that is why you see here, you're able to plot. You use your compass to draw the cycles. As we draw the cycles, you see that this very one is between 4 to, we have 4 here to 15, and the second one is 15 to 20, 20 to 25, and 25 to 35. That's why this one is larger. So when we now look at the table we have here, you see that we have for the knots we have 2.4, 0.4, 0.1, or 0.1 and 0. So You can see here 2.4, 0.4, 0.1 and 0. There's nothing here. So for the next one, which is north-northeast, let's look at the north-northeast. You can see for the north-northeast, north-northeast, what do we have there? We are supposed to have here, let's see what we have. In north-northeast, we have 3, 1.2, 1.0 and 5. So 3, 1.2, 1.0 and 5. So we continue to enter these values, use these values to fill up these windows. So after we are through with it, we will have to do it for other sectors just as we have them here. And you have them, you put in everything. You can see north-northwest. Here we have 1.7, 0.9, 0.1 and 0. So north-northwest, you can see it here, 1.7, 0.9, 0.1 and 0. There is nothing here. All these ones are 0. That's why there is nothing written here. So the next thing we need to do is, using the windows, the template we have here, we will superimpose it here and continue to rotate it. While looking at what we have here, we try to add up what we have in the area superimposed or covered by the templates, as we have in this diagram. You can see in this diagram we have this. So you can see as we put in the template, which we set the center of the template, and we rotate it along the windows, so you can see that there are values we've gotten here. So this is where we have the maximum or the highest amount of wind blowing, because in this direction, which is 9 to 27. So you can see if you add up everything here, it gives us the highest magnitude of wind compared to when you rotate this up. You rotate this up, you rotate this template this way, or you move it this way, whichever way, you see that the highest amount is. So when we check the magnitude of wind, you know that it is up to 95% of the total wind or blowing throughout the year, represented by these windows. But if it is not, you know that it means that you have to determine another additional direction, which will now serve as the crosswind runway. So you can see we have been able to rotate this very one also. You can see what we have here, and this is the wind coverage for runway. From this one, we're able to have another maximum value. So we're able to get this, and we're able to use this to supplement what we have from the first one. So that's why you can see we have two major runways here. You can see this is the first runway and this is the second runway. The first one is 927, this one is 321. So this very one, wind coverage for runways, these are the two runways. These two runways are provided because the first one fails to meet 95% criteria of wind blowing throughout the year. So we have to determine the second one, which is the crosswind runway. So we must make sure that the combined average is more than 20, is at least more than 95. That is why you see here we said after doing that, we said the combined wind coverage of 96.6% of for the use of either runway is shown in the figure. So that is what is shown in figure 3.5. So this is the combined wind component of 96.6. So that is what we have in this last diagram we have here. So we'll be able to go to open board to look at clearly or to do an illustration of how this can be possible. So this is how to orientate a runway using a windows. Like I said earlier, it involves concentric cycles, which measures from the wind studies or meteorological studies. The concentric cycle represents the magnitude of the wind, while the radial lines shows the direction the wind is blowing. So we are able to plot them using as given from meteorological study, as you can see from this table, and then a template is used. A template with half of it calibrated as 15 miles per hour is used to rotate around the windows until we're able to determine where the largest amount of wind blows. So if we're able to get it from one attempt or from one sector of represented by the template, or from the several sectors represented by the template or covered by the template, just as we have here, you can see these are various sectors that falls in between, because this now shows a runway. You can see the runway. This template represents a runway, but in such a way that the wind speed does not exceed 15 miles per hour. That is why we calibrate half of it as 15 miles per hour, and we rotate it round the windows. As we rotate it round, we'll be able to get where we have maximum amount of wind. It should cover for about 95% of the total wind blowing for the year. So if we cannot obtain that from one single runway, then we need to provide for the second runway as such that the combined total of wind blowing on those two runways should exceed 95% of the year. So that's why, and that second runway is known as the crosswind runway. So this is the first runway we provided, 9 to 27, which is not enough. By checking what is contained, the values that are here, the wind, the magnitude of the wind blowing throughout the year. So we have to provide for the second runway, which is the crosswind runway. This one takes care of the remaining wind directions that are unaccounted by the first one. So with this, we have been able to locate two runways. Where one is the main runway, the second one is the crosswind. One is the main runway, the second one is the crosswind runway. So viewers, this is where we come to the end of today's lecture on runway orientation and numbering. So using metrological studies, using ICAT recommendation, and finally demonstrating on how to use the windows. Thanks for watching. See you in the next video. Bye for now.